Okay, so this is quiz A for the second half of Unit 3 in Trig DC. Convert the ordered pair in rectangular coordinates to polar coordinates. So this started with Unit 7.1, which says that we're going to learn about polar coordinates. When we have a pair of rectangular coordinates, the first thing I like to do is graph them. So 8 root 2 is out this way, negative 8 root 2 is down this way, but the same amount. So I already know that that angle is going to be in between 0 and 2 pi. That's going to be 1, 2, 3, 4, 5, 6, 7 pi over 4s. So, I mean, I can just do that. Now, I do have equations for this. If I wanted to use my x and my y officially in the equations that I had written on the board the other day, those 4 key equations, I would use tan theta equals y negative 8 root 2 over 8 root 2, and that would just be equals negative 1. So I'm looking for the theta whose tan inverse is negative 1, otherwise known as the angle whose tangent is negative 1. When I take the tan inverse of negative 1 though, I get negative 45 degrees, or negative pi over 4. And that's not in the range of thetas that I was asked for. So it gives me this angle. I have to add 360 or add 2 pi to get into that angle. So a couple of different ways to approach that problem. Just make sure that at the end of the day, you're reporting a theta that actually fits into that inequality. Same with r now. They want my r to be positive. So when I do the r squared equals x squared plus y squared, I'm going to actually pick the positive square root of that. However, I also recognize this triangle that has 8 root 2, 8 root 2. This one's going to be root 2 times that, and 8 times root 2 squared is just 8 times 2 is just 16. So I actually know my r is 16, but I could do the math to check it, and I don't know, used up all my space. R squared will equal the square root of 16 times 2 plus 16 times 2, and I can see that that's going to be a, oh sorry, what am I doing? 8 squared is 64. 64 times 2, square root. Okay, I'm going to square this, and add it to the square of this and the square of that, because squares distribute across multiplication, and that's what this is. 8 times root 2 means I'm going to square the 8 and square the root 2. So I'm going to have 64 times 2 times 64 times 2, or plus 64 times 2. So that is the square root of some big number. I'm going to go with whatever 16 squared is, because I know that's what the answer is. Without getting out a calculator, I can't solve that, but I have to do this multiplication. 64 times 2, that's 112, 120? No, 128, there we go. Plus 128, now I have to add those. 256, the square root of 256 is in fact 16, so I'm solid. My r is 16. Write the rectangular equation as a fully simplified polar equation. Describe the shape. Okay, so we're going to have a conversation about this on Tuesday, but I didn't want to leave you totally hanging. We have discussed, and actually in your geometry classes, you were supposed to learn the equation of a circle is the Pythagorean theorem. X squared plus y squared equals r squared. Graphs to a circle with a radius of r. This will be negative r, this will be positive r, this will be negative r. It's a circle whose center's at the origin and has a radius of r. Now we can see that when we do the substitution. The equation, this equation is one of our fundamental back and forth equations. Specifically, it goes from rectangular to polar. So this is going to be replaced by the other side of the equal sign. When I have a scale and two things are equal Anytime I see one side, I can replace it by what's on the other side because they are fundamentally equal. That is identities, that is truthiness. I don't know, that's substitution for you. So r squared equals 81, which can be simplified to r equals 9. Now we don't say r equals plus or minus 9 in this context because in polar equations, it turns out that doesn't matter. This equation is symmetric. Oh, it said to describe all the symmetries. So we're gonna say it's a circle centered at 0, 0, with radius 9, and it has all the symmetries. Right? I could fold it in half this way and it would fall on itself. I could fold it in half this way and it would fall on itself. I could turn it 180 degrees upside down and it would fall on itself. It has origin, x-axis, and y-axis symmetries. So check, check, check. It has all of them. Now, we're going to talk about how to use transformations to describe some circles that are maybe offset a bit from the origin, whose center is not, in fact, the origin, and we're going to talk about that on Tuesday. So, given complex numbers z1 and z2, find z1 divided by z2. Well, when we divide trig forms, this is the trig or polar forms of a complex number, it's actually easier than dividing the rectangular forms because we divide. So I'm going to take this and divide it by z2, which is 8 cosine 7 pi over 12 plus I sine 7 pi over 12. Now it looks like I might have a lot of math to do, but I don't. The modulus is 9/8, so I'm going to get 9/8. And then my angle, I'm going to be lazy and write cis. It means cosine plus I sine of my angle, which will be, I don't actually need that parenthesis. My angle will be the top one, 7 pi over 4, where I start. I'm going to subtract the angle of the bottom one. So it's just that easy. 9/8 cis, whatever this angle is. So to simplify that, I have 9/8, which doesn't simplify, no common factors. Cis, all right, I have to multiply this by 3 over 3 to get 21 pi over 12, or pi over 12. 21 pi over 12 minus 7 pi over 12. Oh gosh, 21 minus 7. Okay, minus 6 would be 15, so 14. 14 pi over 12, but 14 pi over 12, 21 minus 7, yes, is 14 over 12 simplifies to 7 over 6. So 7 pi over 6 is my landing angle. And this is, in fact, z1 divided by z2. Now, I'm not asking you to plot these, but you know that you can plot imaginary numbers in polar form or in rectangular form. So let's do that as a little practice here. So if I was going to plot this is my real axis, this is my imaginary axis. So I'm going to plot 9 cosine 7 pi over 4. So I'm going to go around 7 pi over 4, that's to here, and out by 9. This is that, okay? Which would actually be in rectangular form 9 root 2 over 2, so 4.5 root 2. And this would also be 9 root 2 over 2 I, so 4.5 root 2. So I could get the x and y coordinates here too. But when I take that number, now this line doesn't actually exist there. It's just the point. The line is just describing how far it is from the origin, but this point is 9 cis 7 pi over 12. 12? 4, sorry. Now we need to plot 8 cis 7 pi over 12. 7 pi over 12 is 1 pi over 12 more than half of a pi. So that's going to be right here. Very shallow angle here. 1/12 is half of 1/6, so that's 15 degrees, and I go out 8, so roughly this one is 8 cis 7 pi over 12. Now when we divide these two, I take this number and divide that number, it's a little weird where it lands. It lands at 7 pi over 6, which is over here, and the modulus is 9 divided by 8, so just a little more than 1. So 7 pi over 6, a little more than 1, is like right here. I don't know, roughly. So it turns out that that number divided by that number is that number. There's a little perpendicularity distance thing going on there, but anyway. The graph doesn't really enlighten us much about the operations on those numbers, but you do need to be able to plot them with their real components and their imaginary components. So write the vector v in the form ai plus bj. So that's the rectangular form. This is rectangular form. I'm going to change my color just to make sure I don't get messed up with the rest of it. I want it in rectangular form where v has the given magnitude and direction. So the trig form of a vector is actually instructions on how to make it, right? But we could also go back to the polar requirements. X is, r, or magnitude, times cosine theta, right? X is r cosine theta, y is r sine theta. So this is now A and B if we want to use the nomenclature of the instructions. Magnitude, sine theta. So this goes to root 5 times cosine of 3 pi over 4. 3 pi over 4 is over here. Cosine is negative root 2 over 2. Negative root 10 over, move that. No, that's all one thing. Negative root 10 over 2. I cannot simplify that because there is not a factor of 2 in the top. There's only a factor of root 2. Totally different number. Related, but not the same. It's like saying there's a 4 down here. Yeah, anyway. We're not going to simplify that because one is under the radical and one is not. So be careful with that. This one's also root 5, but now the sign is positive, root 2 over 2. So again, we have root 10 over 2. So if I truly write it in this rectangular form, vector v is negative root 10 over 2 I, and that's an I vector, plus root 10 over 2 j, that's a j vector. So we have the magnitude and direction, we just plug them into x equals r cosine theta, y equals r sine theta, and chew through it to get our horizontal and vertical components. Now we plotted that point over here. The vector is the arrow that goes to it now. Complex numbers are points in the plane. Vectors are direction and magnitude. They are arrows pointing to a point on the plane. So in standard form. So we have finished the vector problem, and we see that if we went to the left root 10 over 2 and up root 10 over 2, we would get to where we expected to be. All right, so this was a little bit of an interesting one. A force of 20 pounds is used to pull a block up a ramp. Now, when we look carefully at this definition of work, it says if D is the displacement vector of an object. So the displacement vector here is up the ramp. It is how far it went up the ramp. Then work done is W, which is the work. Sorry, it's a constant or a scalar value. Notice that it is a dot product and therefore it is a scalar. The work is the force dot the displacement vector D. But we could also think of it as the projection of D, or of F onto D. So the shadow here of it times the magnitude of D, which is a little bit weird because when you simplify that with the formula for projection, It just becomes magnitude times the cosine of the angle between them. And guess what? We have all three of these pieces. These pieces, I don't have to define my F and divide my D in this weird space and dot product them if I can use the other definition of dot product and work where we're multiplying by the magnitude of D. So I don't need to do a projection, I don't need to do a dot product. I just need to multiply the length of F, which is its magnitude, 20 pounds. Used to pull a block up a ramp. If the ramp is inclined, who cares? Force is directed, who cares? Find the work done by moving the block 15 feet. So the magnitude of this one is 15. So plugging it into this formula for work, I get work equals 20, the force, times 15, the distance, times the cosine of theta, which straightens out the whole concept of we just want this piece of it. We need to know that not all of the force is acting in the same direction as the displacement. So this corrects for that. And the theta is the angle between them, which is literally shown to us and told to us. Now this angle turned out to not matter at all unless we went the long way to define F and D and then dot product them. If we had to do that, that would have taken us a lot longer and we would have required that 14 degrees. That's just too much work. If you can find a better formula, an easier formula, then use it, right? So which one do you have all the pieces of? That's gonna be a key to physics too, by the way. Finding the formula that you have all the pieces for, including the one that you're looking for that you are missing. You need to have everything except for the one you're looking for. So cosine of 30, 300 times cosine of 30 is that's the shallower angle, square root of 3 over 2. So it's going to be 150 root 3, or plug that into the calculator to get an approximate, because I think I said, oop, I didn't say how much. So I guess the exact answer is what we're looking for. Now the units of that, because this is in pounds, LBS is weirdly the label for pounds, and this is in feet, this is the units of pound feet. We just multiply the units, the unit label method. So that is quiz A. Hope it helps.